Transformations. Transformational geometry. Transformations were referenced in the below slide from the first unit of geometry. This was the definition Euclid used for congruence. We just used the word moved instead of transformed. Two objects are congruent if they can be moved by any combination of translation, rotation, and reflection so that every part of each object overlaps. This is the symbol for congruence. If A is congruent to B, this would be shown as below. A is congruent to B. Even though the idea that objects are congruent if they can be moved so that they match up is an underlying component of geometry, it was not used by Euclid in the Elements, nor have we used that idea directly in this course so far. Instead, Euclid developed what we now call synthetic geometry, based on the idea that we can construct objects which are congruent. That's what we've been doing so far. The reason for that is that although two objects could look the same, that doesn't prove that they are the same. We would never accept as proof that two figures in a drawing look like they would line up, therefore they are congruent. However, with analytic geometry, it became possible to exactly move an object and prove if all its points lined up with a second object. If so, the objects are congruent. This is transformational geometry. In 1872, Felix Klein created an approach to mathematics based on using transformations to prove objects congruent. Transformational geometry built on the synthesis of algebra and geometry created by analytic geometry. It led to a further synthesis with group theory and other forms of mathematics, which were being developed in more advanced algebra. We will explore this using transformations on the Cartesian plane to prove that figures are congruent or similar. In a transformation, the original figure is called the preimage, and the resulting figure is called the image. In the examples here, let the preimage be green and the image pink. Let's consider various transformations of a geometric figure and develop some new notation to keep the ideas straight. Rigid transformations move an object in a plane without changing its size or shape. In effect, a geometric figure upon a rigid transformation produces a congruent image. The rigid transformations include translations, rotations, and reflections. Non-rigid transformations change the size and/or shape of a geometric figure. Therefore, a geometric figure upon a non-rigid transformation produces a non-congruent image. The non-rigid transformations include dilations. A rigid transformation of a geometric figure is a mapping that results in a change in the position of the figure in a plane. In the game of dominoes, you often move the dominoes by sliding them, turning them, or flipping them. Each of these moves is a type of rigid transformation. This is a translation, which is a slide. Here's a rotation, which is a turn. And here's a reflection, which is a flip. Each of the rigid transformations produces a congruent image. A dilation is a similarity transformation. Generally, a dilation is an enlargement or a reduction of a plane figure. It is the result of a process in which a figure is made larger or smaller in size while preserving angle measure. Here's an example. Here's our original triangle here. Here's an enlargement of that triangle, and here's a reduction of that triangle. It follows that dilations produce similar non-congruent images. Some transformations, like the dominoes, preserve distance and angle measures. These transformations are called rigid motions. To preserve distance means that the distance between any 2 points of the image is the same as the distance between the corresponding points of the preimage. Since distance is preserved in rigid motions, so will other measurements in the figures that rely on distance. For example, both the perimeter and area of the shape will remain the same after the completion of a rigid motion. To preserve angles means that the angles of the image have the same measures as the corresponding angles in the preimage. Transformations. Which of these is a rigid motion? Sliding for sure. Rotating is also a rigid motion. Flipping is a rigid motion. But dilation, size change, is not a rigid motion. So we have translation, reflection, and rotation. A transformation maps every point of a figure onto its image and is described using mapping notation. Prime notation is often used to identify image points. In the diagram below, A' is the image of A. Triangle ABC maps onto triangle A prime, B prime, C prime. Note: you list the corresponding points of the preimage and image in the same order, just as you would for corresponding points in congruent figures or similar figures.